Hello and welcome to the first part of this series of revision clips for the motion topic of the EDEXCEL Physics A-Level course. This is primarily made for the Year 12 students at my college, but this is equally valuable to all. So please like and subscribe to the video. That's what YouTubers are supposed to say. And please do leave me a comment below. Let me know if this is useful to you, what details you want, any questions you might have, and I'll help you out and maybe even shoot a different video expanding on some of the issues raised. All right, so the first thing we have to talk about is the difference between distance and displacement, and in fact the difference between scalar and vector properties as a whole. But let's look at distance and displacement because this is probably one of the easier ones to explain the difference between. So the distance is how far you have gone, and that's a scalar. Okay? We'll discuss what that means in a moment, how far you have gone. And the displacement is the distance and bearing as the crow flies, which means how far have you actually traveled. That is a vector. Now, when I'm in my lab with students, I like to demonstrate this with the following thing. I will start with points A and B. Now, normally in the lab, I will actually start on one side of my desk. I have a pretty wide desk in my lab, and I will walk around the lab in a completely random direction, and I will have a convoluted path around the entire space until I get to the other side of my desk. And I could plot that distance in the following way. I could say that I'm going to move, let's have a look at a three-part journey instead of my meandering, but I'm going to go a distance, we'll call that D1, then I'm going to change direction, I'm going to go another distance, D2, and then I'm going to go a final distance, D3, and that's going to take me from point A to point B. Now, what have I actually done? Where have I moved to? The total distance I have travelled is D1 plus D2 plus D3. That is my total distance. But that's not really how far I've gone. That is how far I have gone, but it's not where I have actually travelled to. If I look at the distance between A and B, I'm actually now in a straight line. That's how far I've actually moved. I've moved from point A to point B. The shortest distance between those 2 points is a straight line. Now this is the displacement. So it doesn't matter what direction you have gone in, as long as you've gone from point A to point B, the straight line with a direction bearing to that point is your displacement. So traveling from A to B, my total distance is D1 plus D2 plus D3, and my displacement is S at 90 degrees. So I have turned 90 degrees and I have walked to point B. So moving on from distance and displacement, we can talk about speed and velocity. Now, it's pretty much the same argument here. Speed is the rate of change of distance. Now we've discovered what distance is. It's the complete journey for how far you have gone. So the speed is the rate of change of that distance. The velocity, however, is the rate of change of displacement. And now let's look back at my example. I've now back at my desk. I'm standing at point A and I'm going to travel to point B. I'm going to do it the same route. I'm going to travel D1, then D2, then D3. But the displacement, of course, is S. Now I'm going to define three different things now. The average speed is the speed for the whole journey. Okay? So that is distance 1 plus distance 2 plus distance 3 divided by the time taken to do the whole journey. You can think of the average speed. My journey to work, I get into my car, I drive to college. I'm not going the same speed all the time. I would be arrested as part of my journey involves the A38, which is a 70-mile-an-hour limit. If I try and drive through my little village at 70 miles an hour, I'm going to kill someone, if not myself, and I'm going to get rightly arrested and banned from driving. So The average speed then is the sum total of all the distances I've travelled divided by the total time it's taken. Nobody asks you when you're at work, how long did it take to get down this part of your journey and then this part of your journey and this part of your journey? They ask, how long did it take you to get here today? Oh, it took about 20 minutes. Okay, unless they specifically want to know about a specific part of the route. How long did it take to get down the A38 today? Oh, that took me about 10 minutes. Okay, so that's the average speed. The instantaneous speed, let's isolate D1. The instantaneous speed at D1, let's say I'm doing a constant speed for that distance. That's D1 divided by T1, which is the time it took to go that short distance. But the instantaneous speed really is the speed that you were going at that specific point. If I get in my car and I'm driving through my village, I'm driving at 20 miles an hour maximum. If you took a snapshot of my car and with the speed, it would tell you I was doing 20. The snapshot of me going down the A38, it would say 70. Okay, that's the instantaneous speed. So the police use these two different measures. Instantaneous speed can be taken by a speed camera. They, if you'll see the speed cameras by the side of the road, normally in residential streets where you have small white gradings down the line. If you drive past a speed camera and you are driving more than the speed limit set, it will activate the camera, take a photo, and then the time of the exposure is known, and where your car is along those lines, they're spaced 2 meters apart. It knows exactly how much more than the speed limit you were doing based on that. That's your instantaneous speed. The average speed, you'll see these going up Howden Hill, for example. Sorry, coming down Howden Hill, for example. Coming towards Exeter, they have an average speed camera. So at the top of the hill, right next to the Esso garage, there is the first camera, and right at the bottom of the hill, there is the second camera. Some motorists, you'll see these guys do this. You're trying to keep an average speed of 70 because you know you're going to get a ticket otherwise. You'll see them zoom past you and wonder why you're driving so slowly down a really fun steep hill, and then you'll see them hit the brakes back to about 70 right in front of the camera. Now, unfortunately, these cameras take your average speed over 2 points, divide them by the total distance between the 2 points, and they work out that you are an idiot, you have been speeding, and you're going to get a ticket and some points on your license. So the velocity, though, that is the displacement divided by the time taken. So if you're taking a wiggly woggly route all the way around the lab, this is what I do with when I'm teaching this to lower school and to anybody. I will walk around the room with a stopwatch in my hand, and I will time how long it takes. If I'm really advanced and I've remembered to pick one up, I'll grab a trundle wheel as well, and we'll measure the distance, and they'll work out my average speed, and then we work out my velocity, sorry, and it always surprises them because my velocity is very much lower than my speed. For some reason, some students think velocity is faster than speed, but it can't be. Velocity is never faster than speed. It's only ever the same if you're traveling in a straight line. That's without any relativistic effects, which we will talk about later on in the course. Right, so let's bring us down to acceleration. We talked about speed as the rate of change of distance, and velocity, the rate of change of displacement. Acceleration is the rate of change of velocity. That's a vector because velocity is a vector. This has very important implications. Because acceleration is a vector and it relies on the change of velocity, which is also a vector, if you are going at a constant speed but change direction, because your vector has changed, you have accelerated. Something has changed your direction. This is a force. A force has changed your direction. It's caused you to accelerate. This becomes very important when we look at circular motion later on in the course. Again, let's have a look at this as I travel around the room. The acceleration is the change in velocity divided by the time taken. So as I've gone from d1, then through d2, then through d3, if I've changed velocity at any of that point, divide that by the time it took to change the velocity, I end up with my acceleration. So acceleration is the change in velocity divided by the change in time, delta v over delta t. We find it useful to look at the initial velocity and the final velocity. Whenever you look at this in GCSE, normally, I say normally, the initial velocity or the final velocity will be 0. It's either going from rest or to rest. At A level, not so much. You're going to have a velocity, initial velocity, and you're going to have a final velocity. So we use two different letters for velocity. We use U for the initial velocity and V for the final velocity. If you're wondering why we use U and V, V is velocity, but U comes before V in the alphabet. So V is your velocity, and U is the velocity you had before that. So let's have a quick overview of some more vector and scalar quantities. Scalar quantities just have a magnitude. So speed, for example, you could be going in any direction you want. 30 miles an hour is 30 miles an hour. However, a vector quantity has direction as well as the magnitude. So if you are doing 30 miles an hour, but you're driving around in a perfect circle, you are constantly accelerating. You're constantly changing direction. So the velocity is constantly changing, even though your speed is the same. And this is very important for circular motion and for orbits. Okay, so here's a quick look at vector quantities and scalar quantities. Velocity, we've discussed, is a vector quantity. Force is a vector quantity. It has a direction. Whenever we look at force diagrams, we're going to be looking at them in specific directions. This is very important because it allows us to resolve forces and work out what resultant forces are in different directions. Momentum, because it relies on velocity, that's a vector. Acceleration, as we've discussed. Displacement, as we've discussed. Magnetic and electric field strength are vectors because they depend on which way the charges are. So it depends on where a positive ion would flow. Remember, you're going to hear this acronym a lot, and I'm going to shout this at you if you are in the physical college with me. I can literally see a couple of my year 13s from this year already covering their ears as I say, WAPID, what would a positive ion do? And that is how you always think about magnetic and electric field strength directions. What would a positive ion do? Because some people try and draw them in the direction of conventional current. Don't do that. Weight is a force, therefore has to be a vector. Scalar quantities, charges build up, they have no direction, even when they are flowing. The flow of charge has a direction, but the charge does not. Temperature is just a quantity. Speed, energy, distance, resistance, time, mass, moles, and potential difference. These are all scalars. None of them actually have a direction attached to them. All right, we're now going to have a quick look at motion graphs. Now these become quite important. You would have seen some of these at GCSE, so this is mostly a recap, but let's have a look in more detail now. So we've seen these before. This is the displacement time graph, where S is the displacement. It's measured in meters, time, of course, measured in seconds. So this displacement time graph starts at displacement of 10 meters. And goes for a time of 5 seconds where the displacement doesn't change. So this object is stationary and is stationary 10 meters away from some origin at some point, and is stationary for 5 seconds. Then for 4 seconds it moves from 10 meters to 22 meters away from the origin. Okay. So the velocity of that object is the gradient of the line. So we can see that displacement 10 for the first 5 seconds, it's not moving anywhere. If you take the gradient of that line, it's a horizontal line, the gradient is going to be 0, which is what you expect. It's not going anywhere. The velocity is going to be 0. Otherwise, weird things are happening and the universe is broken. But if you look at the displacement from 10 to 22 meters, the difference in displacement divided by that time taken, those 4 seconds, that's going to give you a velocity. And you can do that by looking at that graph. So you can calculate the velocity at each section of the graph. As I say, v equals 0 there, it's constant, it's stationary, it's not going anywhere. That one though is at constant velocity, it is a straight line, and you can calculate the velocity by doing 22 minus 10, that's the total displacement for this section of the graph, divided by 9 minus 5, that's the total time for this section of the graph, which gives you 3 meters per second. Here now we have another displacement time graph, but you can see that it is curved. You can see that there is a velocity because the thing is moving, and the velocity is increasing. We're getting an increasing gradient. So this means that it is accelerating. The gradient is constantly increasing as the velocity is constantly increasing. So how are we going to find a velocity at any given point? Well, it's simple. Now we do gradient, and we take a gradient at a tangent. We find the instantaneous velocity at that point. So here we go, we'll go for a point there, draw the tangent, and then we can find the velocity there. If we want to calculate the acceleration, then we take 2 gradients at 2 points, that's the initial and the final velocity, and divide that by the time taken to get between those points. So then we have the equation v2 minus v1, or v minus u, divided by t2 minus t1. Velocity is displacement divided by time. The average velocity is taken over a period of time. The instantaneous velocity is the velocity at that specific moment. And so if we look at displacement time graphs, the average velocity for the points between this first pink graph could be drawn as this straight blue line. The instantaneous velocity, though, is the tangent at any point of that graph. Okay, so let's very briefly look at the part of this exam question here. What you'd be given is this displacement time graph, and it would say explain the sections of the graph A, B, and C. So you'd have to talk about the different sections of the graph. Section A, the velocity is clearly increasing. The rate of change of displacement, the velocity is increasing, so therefore that implies an acceleration. Part B, you can see that the rate of change of displacement is constant. It's a constant line. That means the velocity is constant, and therefore the acceleration is 0. There's uniform velocity. And at C, the displacement is not changing with time. Therefore, obviously, there is no change in displacement. It's stationary. It has stopped. Okay, so moving on to velocity time graphs. You have to be really careful when you're looking at motion graphs. Look at the axes. Always look at the axes just to be sure what it is you're looking at. This is a velocity time graph. If you have a straight line, then you have a constant rate of change of velocity. Therefore, you have an acceleration. If you have a horizontal line, you have a constant velocity. So the gradient shows the acceleration in the same way that the gradient of the displacement time graph shows you the velocity. The gradient of the velocity time graph, because to calculate the gradient we would have to do the velocity divided by the time, dy by dy by dx. So that gives you the acceleration. The area under the line, if you took the area under these parts of the graph, that shows you the distance travelled, because then you're multiplying velocity by time to get the area, and that's going to be the distance travelled. If you have a negative velocity, that means you've changed direction, and you end up with a negative displacement because they're vectors, which means that the acceleration is backwards. It's still a positive acceleration. It's not necessarily Apologies, my mic cut out there, so I'm not sure what happens, but as we move on, so this is just this a little bit clearer. The blue line is a constant acceleration because it is a increasing velocity over time, and it has a constant gradient. This makes it a constant acceleration. The beginning of the red line is also a constant acceleration, and then you get to the horizontal part at the top. That is a constant velocity. And then as the velocity comes back down towards zero, this is a constant deceleration. Okay, so we'd be asked the same question again to explain the sections of the graph of the velocity time graph. Remember, look, it's exactly the same graph, but the axis is different. Instead of an S for displacement, it's now a V for velocity time. It would be that simple. It may not even have velocity time written on the top. We just have that V on the y-axis. So part A, you have an increasing rate of change of velocity, and that shows that the acceleration is increasing. The acceleration is getting more and more, larger and larger. B, you have a positive constant gradient, which means that the acceleration is uniform, so you have a constant acceleration. And then at C, we have a uniform velocity. Okay? The distance time graph, we had a stationary object. Now we have a constant velocity, and no force is being applied at this time. Now, if we look at an acceleration time graph, the gradient is now the change in acceleration, how quickly the acceleration is changing. The area under the line, that shows the change in velocity. So you can see that the curved line in that first graph there, that is a constant negative acceleration. That means it's decelerating. That's a displacement time graph. So the gradient of the displacement time graph is positive and decreasing by the same amount each time. You can see that the acceleration is becoming less. If you transfer that over to a velocity time graph, you have a constant gradient, but negative one. That means that it's exactly the same. It is a negative constant deceleration. And then if you apply this to an acceleration time graph, you have a horizontal line in the negative area, which means that obviously it's decelerating. All right, so let's have a look at what these look like by looking at a bouncing ball. Now I'm going to apologize for the animation for this. I didn't actually create this, but there is a section at the bottom of the bounce where the ball deforms, and it exaggerates a little bit the time it takes for this deformation and then the elastic rebound, which causes it to bounce. Okay, so here we go. We have a squashy ball, and it's dropped and it bounces 3 times. So there it goes. The ball drops. There is a deformation at the bottom, and then it relaxes and then returns back into the air, and then comes down, deforms, bounces, back up again, each time going back to a different height on its third bounce. And you'll notice when you look at the graphs, each of these deformations gets longer and longer. And this is true. We just don't notice this because this is where the energy is lost, but we don't see it in real time. But if you slow down footage of a bouncing ball, then you'd see it. There are some amazing videos out there of golf balls landing or being impacted. I recommend you go and look at them. So what would our graphs look like? A displacement time graph, a velocity time graph, an acceleration time graph. So let's have a look. The first one is a displacement time graph. As you expect, the displacement follows the path of the ball. It stops at the bottom, displacement becomes 0 for a short time, and then reflects back up again, reaches its peak, comes back down, ball bounces, gets longer, goes back up, doesn't go as high because of energy lost, and then bounces again, takes a longer time. This is wildly exaggerated, and off it goes. So the acceleration, obviously the acceleration is the same. It's acceleration due to gravity, so it's 9.81 meters per second as the ball falls, but the displacement falls from its maximum displacement all the way down to the bottom. Then you get the elastic deformation, and you're going to get some energy loss there. If you drop a ball, it makes a sound, it makes a squishy sound, some heat is generated, and so we lose energy. And so as all of that kinetic energy then gets converted back into potential energy on the way up, it then stops, all converted to potential energy, then drops again, converts back to potential energy, and so on and so on. And so now let's look at a velocity time graph. Our ball starts falling, and the velocity is going to be negative. It's going to be increasing, but it's going to be heading towards the floor, towards the center of the Earth. So we're going to declare that negative. So off it goes. The velocity is increasing, becomes negative, and then almost immediately it becomes positive again as it increases, and then it gets to its peak. The velocity becomes 0, becomes negative again, and then positive, 0 as it reaches its peak, then back down, bounces, and then straight back up again. Okay, so we get this kind of sawtooth looking graph with this bouncing ball. Instead of the beautiful curves we got from the displacement graph, we've now got this kind of sawtooth effect. So let's have a look at the acceleration graph. The acceleration time graph looks a little bit like this. We have a constant acceleration at minus 9.81. Then we have an immediate acceleration as it heads upwards in a positive direction, but then it's always accelerating back towards the center of the Earth. So we have a negative 9.81 acceleration. We only have a positive acceleration at the point where it's bouncing. Okay. So that's not immediately obvious, and as you can see, these time periods where it bounces, even though these would be infinitesimally small, this is exaggerated. They get longer and longer each time, and smaller and smaller. You get a smaller acceleration heading towards the opposite direction, coming back up. Okay, so we're going to move on now to Newton's laws. We're going to examine Newton's laws of motion and what they mean for A-level physics. Okay, so the first thing we're going to do is remind ourselves of Newton's second law, where is force equals mass times acceleration, provided the mass is constant. Now we're going to look at different forms of this equation at some point through the course, and we're going to look at what this actually means in terms of momentum, in terms of change of mass, in terms of change of acceleration, all kinds of things. But for now, let's go back to our normal definition of force equals mass times acceleration, F equals ma, that very famous second law equation. And we can do a practical where we vary an applied force by keeping the mass constant, and we'll notice that the acceleration is always proportional to the force. We will do this in the lab with an air track and trolleys, and we will do various forces pulling those trolleys through light gates. And then we can vary the mass, keeping the applied force constant. This is the one we do at GCSE, and we notice that the acceleration is proportional to 1 over the mass. Okay? And then we can put these together and verify that F equals to ma. Let's consider for a moment we're in a lift. When you're at rest in a lift, let's say you're standing on the scales and it shows 810 newtons. Certainly wouldn't if I stood on the scales. It would be vastly more than that, but let's see that someone who weighs 81 kilograms, mass 81 kilograms, stands on the scales, weighs 810 newtons. When the lift goes downwards, what's actually happening? Well, to start off, you're accelerating. There is a force on you. There has to be because you're accelerating. So the scales are going to be reduced. They're going to show 775 newtons. When the lift goes back to a constant velocity, the scales will show 810 newtons again. And then as the lift slows down, when it gets to the floor, your scales go up. They're going to show 850 newtons. That's traveling downwards, but when you're traveling upwards, the opposite occurs. To start with, you're accelerating upwards, and so the scales are going to show 850 newtons. When it's at constant velocity, the scales show 810 newtons, and then deceleration occurs, and then the scales show 775 newtons. Why is this? Okay, so when you're in a lift, your apparent weight changes, as we've just seen. But why? When you're not accelerating or decelerating, when you're at a constant velocity or stationary, you see the actual weight. But the force measured by the scales, that's the contact force of the person, not necessarily the weight. It equals the weight when you are at constant velocity. So the contact force changes when accelerating or decelerating. Now let's for a moment actually clarify the middle point. The force measured by the scales is contact force of the person, not their weight. We're going to be assuming that we are not at very high speed. When we get into relativistic physics, you're going to see why that's important, because mass can change at different speeds. But we're going to assume that that is a minimal effect right now. Okay, so we can explain the changes like this. This free body diagram represents the person standing on the scales. The scales show 810 newtons. That is a contact force. The weight equals the contact force. That is 810 newtons. Remember, the scales are measuring that contact force, not the actual weight. So Newton's third law says that the scales push up with a contact force of 810 newtons, and that matches the 810 newtons of the person's weight. The resultant force is 0, and according to Newton's first law, we're not moving, or we're at a constant velocity. So the body is at a constant velocity. Now then, the scales will show 775 newtons. That's the contact force. However, the weight is still 810 newtons. Your weight doesn't change. It's an apparent weight. It's the contact force that's changing. So there's a resultant force now of 35 newtons. Newton's second law tells us that the body is accelerating. There is a resultant force. There is an acceleration. So the body weighs 810 newtons. The mass is weight divided by acceleration due to gravity, which gives you 82.57 kilograms. And so acceleration is force divided by mass. We can calculate the acceleration then. There's 35 divided by 82.57, whereas 35 is the resultant force, and that gives you an acceleration of 0.42 meters per second per second. Okay, so now the scales show 850 newtons. Again, that's the contact force. The weight is still 810 newtons, but now the resultant force of 40 newtons in the opposite direction. Newton's second law still tells us that the body is accelerating because there's a resultant force. Force is mass times acceleration. So again, the body weighs 810 newtons, the mass is 82.57 kilograms. So now the acceleration is 40, which is the resultant force divided by 82.57, which is 0.48 meters per second. Remember, this is a vector, so there is a negative on that, or there should be a negative on that. So that's a minus 0.48 meters per second. Okay, so let's have a look at multiple body force scenarios. We just looked at one body in a lift, where the frame of reference of the lift moving showed an apparent change in weight. There was actually a change in contact force. Let's imagine this train. This train is moving with a driving force of 60,000 newtons. There is, of course, a frictional force of 20,000 newtons, 20 kilonewtons. The driving force is the force of the track on the wheels. The frictional force acts in the opposite direction. The mass of the engine is 150 tons. Each carriage weighs 40 tons. What is the acceleration of the train? How do we work this out? So the first thing we need to do is calculate the resultant force. You take the driving force of 60 kilonewtons, take away the frictional force of 20 kilonewtons, and you end up with 40 kilonewtons. 1 ton is 1,000 kilograms. So the total mass of the engine plus the carriages is 150 tons plus 2 times 40 tons, giving you 230,000 kilograms. Force is mass times acceleration, so acceleration is force divided by mass. So we now have a resultant force and we have a mass. So we end up with 40,000 divided by 230,000, which shows that this train with this setup is accelerating by 0.174 meters per second per second. Okay, so let's for the moment focus on just the carriage in the middle. So here it is, this carriage in the middle of the train. Let's have a look at the forces involved on this carriage. The first one is you have T1. This is the force of the engine pulling the carriage along. And then T2, which is the force of this carriage, the force of the third carriage on this carriage. You still have a frictional force. So now you can see that T2 and the frictional force are acting in the opposite direction to T1. So T1 is the tension of the forward coupling, T2 is the force of the backwards coupling, and then F is the frictional force. We know that the acceleration is 0.148 meters per second. Write an expression for T1 minus T2. Okay. So to do that, we add the T2 and F as one negative force. So we have T1 minus T2 plus F gives the resultant force, which is equal, of course, to mass times acceleration. Now we know that mass times acceleration, it weighs 40 tons, and the acceleration was 0.148 meters per second. And therefore, T1 minus T2 plus F equals 5,920 newtons. This is fine, but we were told to find an expression for T1 minus T2. So the force for friction was 20 kilonewtons divided by all 4 vehicles, and that gives 5,000 newtons per carriage. Apologies, the army are doing an exercise again. It's the joys of living in Dartmoor. So T1 minus T2 minus 5,000 gives 5,920 newtons. Therefore T1 minus T2 gives 10,920 newtons. Okay, so let's look at another example, and this is one where I'm going to give the example to you, and I'd like you to pause the video, have a go at it yourself, and then we'll work through the answer. So let's consider a car of mass 800 kilograms, and that's towing a caravan of 300 kilograms along a horizontal road. Resistant forces, let's assume they're constant, on the car and the caravan are 700 newtons and 1200 newtons respectively. So A, the car exerts a driving force of 3,000 newtons. What is the acceleration of the system and the tension in the coupling? B, find the tension in the coupling when the system is travelling at constant speed of 60 meters per second. And then C, find the tension in the coupling when the car exerts a braking force of 2,000 newtons. Alright, so let's have a look at part A. We have a car of 800 kilograms towing a caravan of 300 kilograms. We know that the car exerts a driving force of 3,000 newtons, so we have to find the acceleration of the full system and the tension in that coupling. First thing we're going to do is we're going to label all of the forces acting in the horizontal plane. The car has a driving force of 3,000 newtons. There is a 700 Newton friction force, and the caravan has a 1,200 Newton friction force. So, to calculate the tension, we're going to need to consider the entire system as a single unit, so that we can calculate the acceleration, and then we can calculate the tension. So the acceleration works on all objects in the system. So the resultant force, we've got 3,000 newtons in one direction, we've got 700 newtons plus 1,200 newtons in the opposite direction. This gives us a resultant force of 1,100 newtons. Force equals mass times acceleration, therefore acceleration is force divided by mass. That gives you 1 meters per second per second. The acceleration acts on both the car and the caravan, so now we can focus on just the caravan and look at that tension force. We can ignore the car for a moment. The resultant force acting on the caravan, mass times acceleration, is now 300 newtons. We have 300 kilograms multiplied by acceleration of 1 meter per second. To get the resultant force of 300 newtons, the tension must equal 1,200 newtons, which is the friction force, plus the 300 newtons of the driving force, and that gives you a tension force of 1,500 newtons. So B, find the tension in the coupling when the system is travelling at a constant speed of 60 meters per second. So let's consider for a moment, what does the force provided by the tension actually do? What's actually happening here? So this force is holding the objects together. If the first one is accelerating and pulling the second one, the tension has to be a greater force than any resistive force is to apply a resultant force. Otherwise, the second object just isn't going to accelerate. But we are traveling at a constant speed, so there is no resultant force. So the tension is going to have to pull the second object so that there is no resultant force. So we're going to have to balance all the forces. So the tension has to be the same as the resistant forces. So in this example, the tension is 1,200. So now we can focus on the tension in the coupling when the car exerts a braking force of 2,000 newtons. So I think I've been calling that 20,000 for a while. It's 2,000. So the same thing again, we're now going to label all the forces acting in the horizontal plane, and we're going to assume that the resistive forces are constant at the immediate time of braking. So again, we're going to draw all of the forces, but this time they're all going to be in the same direction. We have the braking force of 2,000 newtons. We have the resistance, the friction of 700 newtons on the car, and the 1,200 newtons on the caravan. So the resultant force is 700 plus 1,200 plus 2,000, which gives 3,900 newtons. Again, acceleration is force divided by mass, which is the total mass of the system, and that gives you 3.55 meters per second. So the resultant force on the caravan, that is the mass times acceleration. We know the acceleration now is 3.55 times 300 kilograms, which gives a force of 1,063.6 newtons. Now remember, we're trying to work out the tension. The tension is now 1,200 newtons minus 1,063.6 newtons, which gives a tension force of 136.4 newtons. Okay, so when we're looking at these examples of tension, if a vehicle or an object is moving at constant velocity, then the tension is the same as resistive forces. There is no overall resultant force. Otherwise, it would be an acceleration. And Newton's second law says Newton's first law says that's not true. We're at constant velocity, so there's no resultant force. So tension is the same as resistive forces. If an object is accelerating, the tension has to be greater than the resistive forces so that it can go faster than it was before it can accelerate. So the tension is the resistive forces plus the accelerative force. That's the resultant force. So you can't start by calculating acceleration of the whole system, then use this to calculate the resultant force acting on one part of the body. So let's look at this train question. You have 3 seats, seat A, seat B, and seat C. Seat A, the passenger is sat opposite seat B, and seat C, you're in airline configuration, sat behind seat B. Okay, normally there'd be a table in between there, say A and B, but we're just going to ignore that for a moment. We're traveling in the direction where seat A is going in the correct direction, and passenger seat B and seat C are traveling backwards. So we're moving at high speeds in this direction. Seat belts are not used on trains. Okay, that is a fact. So using reference to Newton's laws of motion, explain which seat is the safest in an event of rapid deceleration. Okay, which one of these 3 is going to be the safest in the event of a rapid deceleration? The train all of a sudden slams on its brakes, something blocking the line, and it's going to stop suddenly. Well, it's not going to stop suddenly, but it's going to decelerate rapidly. Pause the video, and I want you to try and work out which of these seats is going to be the safest. Okay, so using Newton's laws of motion, passenger A is going to carry on. Newton's first law says that an object at rest remains at rest. That's acted on by an external force, but this passenger is not at rest. He is traveling at high speed on the train. He has the apparent appearance of rest, but if that train all of a sudden decelerates without a resultant force acting on him, he will carry on moving at the same speed as the train until he hits another object, in this case passenger in seat B. So off he goes. The train experiencing the decelerating force, passenger A is not restrained, so he's going to carry forward. Doesn't experience the braking force. Okay. So passengers B and C are going to remain in their seats. They're experiencing the braking force and they are going to be fine, except for passenger B is going to get squished. So bang. So passenger A is going to collide with passenger B. So passenger in seat C is the safest. Okay, so students from my college are now going to complete some questions on Microsoft Forms, but please come back, subscribe to my channel, hit the bell notification for the next part in the series of this. I'm going to do all of the recap for motion, and then what I'm going to do the next ones, I'm going to sequentially go through the course and fill it in as we go along, and then I'm going to continue doing the year 13 bits and pieces as well. All right, so stay safe. Oh, don't forget to comment below. Let me know what you want to see, what you want me to do. Obviously, I'm going to go through some exam questions. On this channel, there will also be some GCSE stuff, and there will be some fun experiments and things for kids to do as well. I'm going to try and do some experiments with my kids. not experiments with my children. That sounds wrong. I'm going to do experiments with the aid of my children. They're going to be helping me. There we go. They're like my lab assistants. All right, so stay safe and I will see you soon.